In the remaining two lectures of this course, what I'll try to do is I'll try to demonstrate the versatility of the finite element method. So to do that, we will take two problems, one in heat transfer and one in fluid mechanics, um, where where we'll show that all you need to know is the governing differential equations that you have to solve and the boundary conditions. Once you have that, in most cases, you will be able to set up a finite element procedure to solve the problem. And you will, if you have a code which solves, say, problems in linear elasticity in solid mechanics, minimal changes to that code will allow you to solve a problem in heat transfer or fluid mechanics or electromagnetics. That is the robustness of the method. That is the power of the method. So let us take heat transfer and let us complicate the problem a bit, but by assuming that the heat transfer is steady state, but heat transfer is taking place through an anisotropic material. What that means is that the conduction coefficient, the conductivity of the material, is a tensor represented as a matrix. We are keeping ourselves confined to two dimensions for simplicity, two-dimension steady state. So it is a matrix which has symmetry, but the conductivities are different in different directions. In that case, the governing equation in two dimensions is the heat conduction equation given by this. For steady state, if you don't have steady state, you have some transient terms here, but we are omitting that. Also, the Fourier's law of heat conduction gives you that the heat flux, which is qx and qy in the two direction, heat flux is a vector, is connected to the temperature gradients, the gradients of temperature Tx and Ty, through this anisotropic heat conductivity. And this we are going to write as vector q. This we are going to write as a matrix kappa, and this we are going to write as a vector which we are going to denote by grad t. So this grad t is just t comma x, t comma y put in as a vector. So finally, you have this matrix equation which forms your constitutive equation connecting the heat flux to the gradient of temperature and embodies the Fourier's law of heat conduction. This probably you have already encountered in your heat transfer courses. Now, if we have a body V with normal N as usual, and the heat flux is Q, then we can have at the boundaries different kinds of boundary conditions set up. So we can have a part of the boundary on which this heat flux is specified. So the normal component of heat flux, that is Q dot N, which we are going to call Qn, is specified as Qn bar. So we call that part of the boundary delta V1. We can have a part of the boundary which we will call, we call this delta V2. We can have a part of the boundary which we call delta V1, over which T equal to Ts is specified. And then we can have another part of the boundary. Then we can have another part of the boundary which we call del V3, on which Qn is again specified, but it is specified as a convective heat transfer equation. So the ambient temperature is T0, the temperature just inside the surface is T. So Qn is some convective heat transfer coefficient H into T minus T0. So these are all things that we have learned in our heat transfer courses. So delta V1, delta V2, delta V3 make up the whole boundary delta V, and there is no overlap between them. Just like traction and displacement boundary conditions, we also have completely disjoint parts of the boundary having one of these three kinds of boundary conditions. So what is q dot n? Q, remember, q is a vector which is del t del which is qx e1 plus qy e2 into d. This is the kind of vector it is. And then q is related to the temperature gradients. Qx is minus kx tx plus kxy minus kxy ty. So so qx would be minus of kx del t del x plus kxy del t del y e1 minus qy is kxy del t del x plus ky del t del y e2, and q dot n is another vector 2D, which is nx e1 plus ny e2. So q dot n is what we have written here. So qn, this is the heat flux out of, so influx is taken to be positive, outflux is negative. So this is either influx or outflux of heat at the on the part delta V2 of the boundary. So in well, this is the influx or outflux everywhere on delta V2. This quantity is specified as Qn bar. Okay, so we have these three boundary conditions that would be applicable. Now, we have already handled a subset of this problem. We have handled the case where Kx is equal to K, Ky is equal to K, and Kxy is equal to 0. In that case, we have isotropic heat transfer equations, and in those cases we have in that case we have seen that this equation where this is equal to k, this is 0, this is 0, and this is k as well. This basically boils down to del square t del x square plus del square t del y square equal to 0. We have handled this equation before, and we know that this is an equation that is amenable to um, creating a weak form pi variational 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 statement, which would look like this. We have already uh, done this when we learned about variational calculus. So for the isotropic and homogeneous case where k is not a function of x or y, k does not vary from point to point and is isotropic, in that case this equation reduces to the Laplace's equation, and for the Laplace's equation we know that this is the variational statement. We have done it before, but in this case for an isotropic case it's a more general case, and we will use the Galerkin method to form the weak form. So we will start from here. We will start from the differential equation. We'll use the Galerkin method and we will try to get the weak form. For the Galerkin method, remember we have to choose basis functions. In our case, when we do finite element, isoparametric finite element, the basis functions are the shape functions themselves. We take them as the basis functions, and we will use that in order to convert this equation, this differential equation, into its weak form. Remember, in Galerkin, we form the residues by multiplying this with the basis functions. So this is what we are going to do. So first, we are going to make the assumption that we always do, the interpolating assumption that Txy, the temperature, which is a field variable in this case, there's only one scalar field variable, so there is 1 degree of freedom per node, and that will be interpolated in the usual way using our shape functions. The shape function character would depend on what kind of element you are using. let's leave that open for the moment. And then once you have this, you can easily see that del t del x, which is del t del x and del t del y, which are my stress-like variables in this case, derivative variables, would be given by del n1 del x t1 plus del n2 del x t2 and so on. Then del n1 del y t1 plus del n2 del y t2, so on, which can be written as del n1 del x del n1 del y so on times the vector of nodal degree of freedom values, in this case values of the temperature at the nodes. There's only one, and you can see that this will be called the B matrix. This will be called the B matrix, but the structure of the B matrix in this case is different from the structure of the B matrix we had in case of a 2D solid mechanics problem, linear elasticity problem. The reason was that in that case, what I called as my strain matrix, this is like my strain matrix. What I called my strain matrix was del u del x, del v del x, del y, and del u del y plus del v del x. So firstly there were two field variables, and then the strain, what we call the generalized strain, was different set of different combinations of the derivatives of the field variable than what we have here. So depending on what are the derivatives of the field variable you need, you will have an appropriate B matrix. You will have an appropriate B matrix. And in the present case, these are the derivatives that I need. So this is my B matrix. Okay. And once you have the B matrix, you can put down the Fourier's law of heat conduction, which was Q equal to, so this is the vector that I had called grad T. So it was kappa times grad T, which is same as kappa times B times T. So this is like your stress strain relation, where you have now related the nodal displacement, generalized displacement vector to the stress at a point. So the Q takes the role of the stress, and this vector takes the role of the nodal displacement. So you can call this a generalized displacement, you can call this a generalized stress. Okay, so this can be easily done, and once this is done, let us formulate the weak form. So for every element we use in place of the phi's that we have in the Galerkin, we use the shape functions themselves. So this is my weak form. This is my weak form, and I have a constitutive equation for Q's. I'll use that later, but right now let us manage this weak form and try to simplify it a little bit. The way of simplifying is using the divergence theorem as always. So I have this volume integral ni, let's say del qx del x dx dy. I do integration by parts, which is the same as the divergence theorem. So I break it up into del x of ni qx minus del ni del x qx times dx dy. So this is amenable to the divergence theorem. So this becomes a surface integral over what we call SE. SE is the surface of the element, and then because you have del x here, you will get nx. So ni qx nx ds, and this remains as a volume integral. So you have del ni del x qx dx dy. Now you will get, I have used this term. When you use Ni times this, you will get a surface term, which is Se Ni Q Y Ny ds. So um, together, together, this has to be set to 0. So this will be set to 0. So uh, you will have del Ni del x qx plus del Ni del y qy. So the first term coming from this and the second term coming from this times this. So these two terms dx dy, the volume integrals on the left, equal to the surface integrals. So this surface integral and this surface integral on the right. Now this surface integral can be broken up into three parts. So if the element shares an edge with del v1, then qx nx plus qy ny is equal to qn, right? So that's what we use. If it shares a edge with del v2, then qx nx plus qy ny is given as qn bar, so replace it with qn bar. And if it shares an edge with del v3, then qn is given as h times t minus t naught, so I use h times t minus t naught. All three possibilities are there. If it does not share an edge with any of del v1, del v2, del v3, the corresponding term will be dropped. Okay, so this is my final weak form of the problem, which I derived from the derived by the Galerkin procedure. I could have derived it by direct variational methods as well, but well, I chose to do it in this way. Okay, I would have reached the same set of equations because these are the basic governing differential equations are symmetric and complete. Okay, so now once I have this, I have to just plug in the finite element approximations. So this would, I would write it as del Ni del x del Ni del y times qx qy. That's the first term. The second term, so each of these terms would be written in a similar way. So once I have this, I will call this n transpose q. Q, I have already seen that q is minus kappa bt. So this would be, sorry, this would be b transpose q. So this would be b transpose kappa bt, and these terms would also have uh, similar discretization. So this is the term that multiplies the nodal temperatures, but there is another term which has nodal temperatures, which is this term. So here also you will have to use nt in place of this t here, and this will also come to your left hand side. So when you put terms together, then you will have a term which has which is b transpose kappa b, which is very similar to b transpose cb that you have in linear elastic problems, except that the structure of b and the structure of kappa are different. You will, in this case, because of convection, you will have another term in the stiffness. So your stiffness would now be this whole thing. This will be your ke, and this whole thing will contain this h times n transpose n term as well, and that comes from this term in the convection equation. Okay. Also remember that this is integral over the surface and not the volume. This is an integral over VE. This is an integral over S3. This is an integral over S1e. This is an integral over S2e. I'll correct this in the notes. This is S3. So these are integrals. These are the integrals that you will get, and these are the integrals that you will now have to evaluate. The Once you have this part, uh, the evaluation is exactly the same as you have done in solid mechanics. It's indeed same in all problems. Now what you will do is you will choose a kind of element. So let us choose a Q4 element. Then Txy is given by the four shape functions N1, and these shape functions are functions of R and S each. And then you will use the chain rule. You will say that del T del R is equal to del T del X del R plus del T del Y del R, which means that del T del R del T del S is equal to J times del T del X del T del Y, and therefore del T del X and del T del Y are J inverse times del T del R del T del S, which is pretty much what we have done in the linear elastic case as well. So in this case, you can write the del T del X as J inverse times this whole row, and J inverse times this whole row as del T del Y, and you have connected the gradients to the derivatives of the shape functions with respect to R and S and the nodal degrees of freedom. And then you calculate K1 as an integral from -1 to 1 volume integral, and then this J comes into picture, J dr ds, because of the linear transformation from the parent to the physical element. So that is very much the same as what we have encountered earlier. Now the stiffness part K2, which is actually a surface integral but contributes to the stiffness, has to be again dealt with in the way we have dealt with surface integrals before. So so we will assume that for the Q4 element, so this is my Q4 element, this is the parent, and let's say that S3 coincides with this edge, which is the edge S equal to +1. This is R, this is S. So this edge is S equal to +1. So if we assume that, then we have to calculate now N transpose N H T, and we will have this surface Jacobian, which we have discussed before, this how to calculate this surface Jacobian, and this is the calculation that we will have to do now from R going from -1 to 1, because we are doing this on a surface where S is equal to a constant, S is equal to 1. So we calculate N's on the surface S is equal to 1, and then we also calculate this surface Jacobian. I'm leaving it as an exercise for you to prove that this, for the case of the edge with S equal to +1, will boil down to this particular matrix. Similarly, you will do it for R3, which is this, also comes from the uh, from the convection term on the right hand side, and this is how we would do it. Again, I leave it as an exercise for you to prove that this is what it's going to be for the Q4 element. Okay. Um, now, now if I had an axisymmetric situation, then things would be slightly different, but still 2D axisymmetric and 2D, the situation that we have done here in Cartesian would be, can still be coded in the same code, in the same element routine, with with minor changes. Remember, we had to do some changes for axisymmetric in linear elasticity also. Here also we'll have to do it because the structure of gradient of t is different. So the gradient of t in tensor form would be del t del r. There's 1 by r del t del theta and then del t del z. These are in the r, theta and z directions. And if you even if you take axisymmetric case, then del theta equal to 0. So this goes to 0. And in the RZ plane, you have this equation. You have this equation for heat transfer in the RZ plane in the isotropic homogeneous case. Okay, this can be handled by using 2D axisymmetric 4-noded Q4 elements, and this can be converted into a variational principle quite easily, and you can use the familiar 2D Q4 elements in axisymmetry in order to solve this problem. I just mentioned this in passing. I'm not going to do this in detail. I'll stop with the heat conduction problem here.